Morning.
Yeah, cam's on everyone. Let's start off. We might extend the class a bit today because we're almost there. We might wrap it up today. And then Friday we can have a break, and then next Monday so we can start off revision. The last thing that we did was EM waves. Hope everyone has started solving something at least. The last thing that we did, polarization. We did that Malus law, and then we saw what happens with the polarites. And the next thing in EM waves is Brewster law. So Brewster law, what this is, when an unpolarized light is incident on a medium, at a certain angle, the reflected ray is polarized. So this is a phenomena which we observe. So let's say we have an interface. So take this as vacuum, and this is mu. This is your normal. So when you send a light ray, you always get a reflected ray and you also get a refracted ray. So unless there's a TAR, right, you'll always get a refracted ray and a reflected ray. And if you look at this thing, this is a non-polarized there. Again, what is unpolarized? You have electric field in all directions. This is unpolarized incident light. This angle is I. This angle is also I. This will be R. When you go from radar to denser, you go towards the normal. And here we get this. This is also unpolarized refracted ray. It actually gets partially polarized, but and here we get a polarized ray. Remember again, what do you mean by polarized? The field is only in one direction. So here the field will be inside and outside of the plane. So that itself is a question. When a light ray is hit at a particular angle, the reflected ray is polarized. So the polarization in which direction? Perpendicular light ray. I mean, they'll say whether it is like this, whether it is in and out, whether it is along the light ray. So there are options like this. E bar is in and out of the plane. Now here, few questions. The first question is this thing. This happens at an angle where tan I is equal to mu. This angle, I is equal to tan inverse mu, is called Brewster angle. And that is the question. What is the Brewster angle? That is one question. Second thing, if you apply Snell's law, 1 into sin I is equal to mu into sin R, but mu is nothing but tan I. Tan I is sin I by this thing. Sin gets cancelled. We get cos I is equal to sin R. We get I plus R is equal to 90 degrees. That means the reflected ray and the refracted ray are perpendicular. So there is a question like this. it is observed when a light ray is incident on a surface, the reflected ray is polarized. What is the angle between reflected ray and refracted ray? If the angle between reflected ray and refracted ray is 90 degrees, then what happens to the reflected ray? It gets polarized. You're getting it? Just play around with this thing. So there are three questions I can ask you. Which direction field is polarized? What is Brewster angle? And what is the angle between reflected and reflected ray? Refracted ray when the reflected ray is polarized. Reflected and refracted ray are perpendicular. That's about Brewster law. Not much, straightforward concept. That is one. So there are three possible questions in this, and they do ask. We don't have any proofs or anything. All these are just experimental things. Next thing. Now, we kept on saying na, electric field is in one direction. True, but what if that electric field is rotating? Meaning, for example, see, let's say you're looking front, then you're looking right, then you're looking back, then you're looking up. Now, if you see, you're always looking in one direction, but the direction is not constant. Getting it? So we have again different types of polarization. So the first thing is called linear polarization. Let me show you what happens. So let's say if you have two different electric fields, I'll also show you a small video on this. Let's say if you take two electric fields, let's say E1 is equal to E naught sine. Here this is traveling in Z direction. So Kz minus omega t I cap. Then we have a second electric field, same amplitude, same phase, but this is oscillating in J cap. So the net field will be E1 bar plus E2 bar. This would be E naught root 2 sine Kz minus omega t I plus J cap by root 2. So basically, when you have two different electric fields which are perpendicular, the resultant will be about an angle, isn't it? In this scenario, it will be 45 degrees. Clear with this? So this is called a linear polarization. Why linear? Because the field is only oscillating in one direction. The direction is one and the direction is fixed. The second case, we have the circular polarization. So just have an idea about this field. It's not really that important, but this is the case will happen when, let's say the fields are E naught sine Kz minus omega t I cap. E2 is E naught cos Kz minus omega t J cap. So if you see them, when you square them and add them, you get a circle. They're out of phase by 90 degrees. Clear with that? So this is the scenario when you get when both the fields are out of phase by 90 degrees. The third one, this will occur when, let's call this thing EA, sine Kz minus omega t I cap. Kz minus omega t plus phi J cap. So here phi must not be 0, then it will become linearly polarized. It should not be 90, then it will become circularly polarized, or pi or any other angle. So the phase angle must be any angle other than 90, or the EA must not be equal to EB. If you satisfy any one of them, you will get an ellipse. Clear this? So how does this look like? The equations that we have.
Sir, EA not equal to EBO.
Not equal to.
Thank you.
Hmm. So let me show you first this.
The polarization of light plays a critical role in
This I showed you last time.
In classical physics, light can be thought of as a wave.
So if you see, right, this is a single light wave which is going, the field is up and down. The green ones are the magnetic fields which are going left and right. So this is actually polarized light. You have field only going in one direction. Let's observe the pink one, ignore the green one, that's a magnetic field.
Electric and magnetic waves.
So let's say first case, you are adding one more electric field in the same direction on top of it.
Space. At each point in space and time, their electric fields will
So if you just add them, right, it will become like E1 plus E2 everywhere. That means both of them are going in same direction. Let's say in this case, electric field is in J cap. The second wave also has electric field in J cap. Then it is straightforward. It will be E1 plus E2. The resultant will be a bigger wave.
The two waves add together to form a new electromagnetic wave with a higher amplitude. Let us consider magnetic waves.
What if you have two waves perpendicular to each other?
But this time, they are...
So the purple one is one electric field, the pink is another electric field. Getting it? Ignore that green thing. The green is a magnetic field.
Not oriented in the same direction.
Look at this. So now you have both the electric fields, same amplitude, same phase. Again, what do you mean by phase? When you go to maximum, I also go to maximum. But the directions are perpendicular.
As before, the electric field will add...
So how do you add the vectors? You join them head to tail and the resultant will be from the remaining tail to the remaining head. So you are moving the vector so that head and tail will meet. And then you draw the vector from the remaining tail to the remaining head. The red ones are the resultant vectors.
And the magnetic fields will add like...
Magnetic fields will be perpendicular to this. These green ones. Now this is how the wave looks. Can you see how the wave is? Every point is at a different angle. It feels like the whole thing is like kind of like a circle.
The two waves add together to form a new electromagnetic wave with its orientation changed as shown.
There you can see that magnetic field thing. It feels like as if it is rotating in a circle. We call it circularly polarized.
Now look at the previous one.
Now look at this thing. Both the waves are in phase. Now what if you make them little out of phase?
The previous one.
To make it perpendicular.
Except that in this case,
but you move it little forward. Now there's a phase angle between them.
Magnetic waves is ahead of the other one.
So you added a +5 phase angle.
Force.
And when you add this, this is how it looks. Now see, when this rotates, you will see how it rotates. It actually forms an ellipse when you do the projection. So
this time
I'll show you one more that. Look at this one. This is the final thing. Are you able to see the rotations? First is linearly polarized. Look at the second one. Second is making a circle when you do the projection. The third one is making an ellipse. So when you actually join the heads of those vectors, what you get is an ellipse. That is called elliptically polarized. This is called circularly polarized, and that is linear polarization. You get a line. So basically, when the wave ka projection, if it is a line, it is linear polarization. If its projection is a circle and an ellipse. I hope the final picture is clear. So you need not know too much about this. Just have this much idea. This is sufficient. I generally won't go beyond this in means. So you should have an idea about what is what. So how will they frame a question? So this was a question someone sent me recently. It's a decent one. Look at this. So this is Ex, Ey. The amplitudes are different, and this would be elliptically polarized. This is sine, and this is cos. This is circularly polarized. This is Ex, Ey. Both are sine, so this is linearly polarized. And this is also elliptically polarized. Clear with this? So if at all they ask you, they'll give you the fields and they'll ask you what kind of polarization is this, linear, circular, and elliptical, and you're done. All clear with this? There, that is about EM waves. So EM waves is this polarization, linear, circular, and elliptical, Brewster law, Malus law, and if unpolarized light passes through a polarizer, it becomes I by 2. So there are 4 formulas in this. Clear with this? क्या हो गया बिहान? Malus law रे. That's about EM waves. The next thing, Vernier calipers and screw gauge. Quite important. Every year you get a question in advance, right? So listen to this thing. It's quite important. Every year you get a question. They mix up these things generally with the errors and everything, and they'll ask you a question. But every year there is one question in advance. Mains may they do ask, but it will be a much simpler thing. So first I will teach you the normal method with the standard Vernier calipers. Then I'll teach you something a more general method, which is actually more powerful and much better. But let's go ahead with this. So Vernier calipers, I'm pretty sure you must have seen something like this. Right? It looks like an axe. When I was in school, we used to take this and we are like, I'm going to kill you. We used to take this and run around the classroom. Like it's an axe and you're trying to hit it. But it really doesn't look this big like a picture. Right? It is the size of your fist almost. It's a pretty small one. So anyway, so if you look at the scale, right, you can see this thing. This is your main scale, which is fixed. Here you have this small thing. This is your Vernier scale, which is movable. So that you can move left and right. And you can clearly see here, we have jaws here. These are called jaws. This is also the bunny ears, and this is the tail. So how does this work? So if you want to measure the outer diameter, put it between the jaws. If you want to measure the inner diameter, then use this ears on the top. If you want to measure the depth of a cylinder, you use the tail. So when you keep the objects there, and when you push it, something happens, the Vernier calipers moves, right? And then we will see how it works. We will see the principle behind it. So first, let's take a standard Vernier calipers. So in a Vernier calipers, we have 2 scales, main scale and Vernier scale. So in a main scale, we have 1 centimeter is 10 divisions. That means each division is 1 mm. We call this thing MSD, main scale divisions, right? The second thing, we have 10 divisions for Vernier scale, but this time the length is only 0.9 centimeters. That means each division is 0.9 mm. This is clear. So you have 2 scales, both have 10 divisions, but the length of each division is not same. So how does this work? Now the concept is pretty straightforward. Why the Vernier calipers works? Listen to this thing. So let's say if I take the main scale, so 0, so this is 1 mm, second, third mm, fourth mm, fifth, sixth, 7, 8, 9, 10. Now if you draw the Vernier has only 10 divisions and 0.9 mm. So this will be 1, this will be somewhere here 2, this will be 3, this will be 4, this will be 5, 6, 7, 8, 9, 10. Do you agree with this? The 10th division of Vernier will match with the 9th division of main scale. Because this is 9 mm, 10 into 0.9, this is also 9 mm. Now, tell me one thing. What is the distance between the first division of main scale and first division of Vernier scale? What is the length of one main scale? 1 mm. What is the length of one Vernier scale division? 0.9 mm. So what is the distance between first and first division? 0.1 mm. What is the distance between the third and third division? 0.3 mm. Distance between 7 and 7, 0.7 mm. This is understood. Now, tell me one thing. If I move this Vernier scale by 0.1 mm forward, little 0.1 mm, which division will match? The first division and the first division will overlap. If I push this by 0.4 mm, then which division will match? This 4 and this 4 will overlap. So if I want the 7th division to match, how much should I push? 0.7 mm. Everyone understood this? Bus, this is the main concept. If you understood this, then you're done. So how does it work? Let's say you keep an object between the jaws and you get a reading like this. Let's say the reading has come like this. Now let's try to understand. We are sure this is 5.0 centimeter, this is 5.1 centimeter, 5.2 centimeter, this is 5.3 centimeter, and this is 5.4 centimeter. Meaning your reading is between 5.3 to 5.4. Okay? Tell me one thing. If the answer was exactly 5.30, how will the picture would have looked? If it was exactly 5.30, shouldn't this 0 here be exactly matching with the 5.3? Do you guys agree with that? If that 0 exactly was on top of 5.3, the answer would have been 5.30. But the 0 didn't match, but the third division matched. That means if it was exactly 5.30, the 0 would have been here. For the third division to match, how much should you push forward? 0.3 mm. That means this distance was 0.3 mm. Makes sense? So the answer is 5.30 plus 0.3 mm 0.03, which is 5.33. Are you clear why Vernier calipers works? Because you took two different scales of different divisions, the distance between them became the smallest length you can measure. Are you getting the point? Because the main scale can measure everything in 1 mm. The second scale can measure everything 0.9 mm. You use the difference between them to measure even smaller than both of them. Is that clear, everyone? I'll give you one more. You tell me what will be the answer for this guy then. There's even a better technique than this. This now it works good for a regular standard Vernier calipers. If I mess up the scale, this thing will go for a toss. Let's say this is 3 and this is 4. Fifth division is matching. What is the answer for this? These things are easy to see and tell actually, you know. This is 3.60 and fifth division is matching. Means you must have pushed 0.05 centimeter, 3.65 centimeter. Easy. Any doubts on this? Clear with this method? Are you clear why Vernier calipers is working? So that is the concept behind the working of Vernier calipers. So that's what I explained here. The distance between the first division is 0.1 mm, seventh division is 0.7 mm. So if you move 0.1 mm, first division will match. If you move 0.6 mm, sixth division will match. So what is the answer for this? So this is 5.2 plus something, and fifth division is matching. So it is 5.25. Easy. What about these two? This is easy stuff. This is like proper mains level or bits level questions. Advanced they don't ask like this. The first thing will be 7.6 and third division is matching 7.63. Yeah, most of you getting it. What about the next one? So if you can clearly see here, this is 7.6 centimeters, and the third division is matching here. This is the third division. So this is 7.60 centimeters plus you must have moved 0.303 centimeter, 7.63 centimeters. This is 3.54 centimeters. All clear with this? Any doubts on this? Anyone not convinced? Like, how did I get? What is the anything that you're not clear? Please ask. Clear. So the main idea behind working of vernier calipers is that we need two scales with different length of the divisions, and the difference between them is used to measure smaller values. That is a concept. And the general formula is main scale reading plus n is the number of division which matches into least count. What is least count? Least count is the smallest measurement the instrument can measure. This is important. There is something called least count and vernier constant. What is vernier constant? One main scale division, one is one vernier scale division. Generally, they both are equal, but not always. So people get confused between a least count and a vernier constant. We will see a problem. So least count tells you what is the smallest you can measure. Vernier constant simply gives you the difference in the length of the divisions. Both need not be same. So people get confused between vernier constant and least count. They use least count, vernier constant in place of least count, and you'll get errors. We'll talk about that also. That is one important thing. This is your general formula. Now in a vernier calipers, right, you have errors. Maybe the equipment is not handled properly, or someone must have dropped it a few times, right? So look at this thing. If there is no error, so when there is no object in the thing, the zero of the main scale should match with the zero of the vernier scale. Such a thing is called there is no error. But sometimes what happens, the vernier calipers zero is slightly ahead and the third division is matching. What is the meaning of this? Even when there is no object, you are showing extra 3 divisions, isn't it? When there is no object, you're not showing 0, you're showing 3 divisions. Matlab, this is a positive error and the correction is negative. So whatever is the final answer, you have to subtract 3 divisions from it. Are you clear with this? So how do you know it is a positive error? They will give you a picture like this. They will say 0, 0 not matching. So if you use this vernier calipers, and let's say you got a reading like this, can tell me for this vernier calipers, if this is the reading when you have an object, what is the answer? So exam they'll ask like this. They will say when there is no object, this is the picture. When there is an object, this is the picture. What is the length of the object or diameter of the object? So you can clearly see this is 6.2. 1, 2, 3, 4, 5, 6, 7. 7 divisions are matching. So technically this should have been 6.27 centimeters. But the error is 3 divisions, so it is minus 0.03. We have to subtract from here. 6.24 centimeters. Clear with this? This is called positive error and the correction is negative. So even when there is no object, you are showing more than 0. You have to subtract it. Clear, no, Purja? Got it, no? 0 is starting from here, no? So answer is between 6.2 to 6 point this thing. Now, there is another type of error. Sometimes what happens, this is 0. Your vernier is actually behind. The vernier ka 0 starts here. What is the meaning of this? What is the error? How much is the correction? This is a negative error, right? This is a negative error. Positive error is when 0 is ahead. It is showing you more. Negative error, it is showing less, isn't it? Now here there's a trap. Listen carefully. If you go back to the beginning, how vernier calipers worked, This was the thing, no? So this was the one, this is the one. Now tell me one thing. You want that 0 to go back, isn't it? If I move this back by 0.1 mm, which division will match? Will the first division match? Then first will come back more. Who will match? The 8th division here and the 9th here will match now. If you pull it backward, the 9th division of Vernier and the 8th division of main scale will match. If I move 0.2 mm, then who will match? The 8th division and the 7th division will match. So if I move 0.4 mm, who will match? 6th division and 5th division will match. If I move 0.6 mm, then who will match? 4th division and the 3rd division will match. Yeah, right, it's not up to scale actually. Are you getting it? Because you're going in the opposite direction, the numbers will not go 1, 2, 3, numbers will go 9, 8, 7. So if this is 0.4 mm, then what is the correction? The correction is plus 6 divisions. You must have moved this 0.6 mm backward. That's why the 0 is behind. Are you getting it? So that means whatever final answer you get, you should add 0.6 mm to it. Is that clear, everyone? Negative errors are dangerous, so we have to be careful with that. Any doubts on this? All sure why the divisions are matching from the back and not from the front? Because if you see Vernier division is behind, if you pull back, it won't match. It will go even farther away. So the numbers will start matching from the back. 9 will match with 8, 8 will match with 7, and so on. Any doubts on this concept? Clear with this? No. This is how you do the problems normally. If you have a standard Vernier calipers, you generally don't have any issue. Answers will come, all great. But if you mess up the Vernier calipers, like they do in advance a lot, they'll give you non-standard Vernier calipers. So there's a better way to do these questions. Listen to this thing, simple concept. This was all that explanation, negative error, positive error, and everything. Now look at the alternate method. Let's say someone gives you a reading like this. Understand the meaning of this. When I put an object between the jaws, can I say like this? The length of the object is the distance moved by the Vernier calipers. Do you guys agree with that statement? The distance moved by the Vernier calipers must be equal to the length of the object. Agreed? Because initially the jaws are touching each other. The distance between them is 0. So when you keep an object between them, the increase in distance must be the distance moved by the Vernier calipers. That statement is clear. Now see, that means if there had been an object here, a rod or something, this number would have been from 0, isn't it? We would have started from 0. This is the length of the object. And now you're telling me the division number 4 is matching. So from here to here, how much is this length? This is 4 times Vernier scale divisions. Do you agree with this length? That is 4 VSD, which is nothing but 4 into 0.09 centimeter or 0.36 centimeters. Similarly, from this point, from the starting till this point, how much is this? That is 7.1, this is 7.5, 7.6, and this is 7.7 centimeters. This will be 7.7 centimeters. Do you agree with that? From the starting of the object till this point must be 7.7. So can I say like this? L plus 0.36 centimeters must be 7.7 centimeters. Therefore, L will be 7.70, 0.36. 4, that would be 3, and that would be 7. Make sense? Are you getting the concept what we did? It's a very simple concept. If the object started from here, this length must be equal to length of the object plus this Vernier length. Simple. The total length must be simply L plus the length of the vernier there. We are simply just doing, there is no big concept, distance between divisions, nothing. Clear with this? So using this method, can you solve this? This method is more superior. You'll understand. If I use even a non-standard vernier calipers, it still works really good. Let's try to get this. Again, don't get confused here. In this case, the main scale is below and the vernier scale is on the top. You can keep it however you want. And how do you know? The vernier scale is always small. You can clearly see it is a small one. So but any doubts on this method, everyone? I hope all are clear with this, what we did, right? The length of the object plus this vernier must be equal to 7.7 because it's starting from there. That's it. That's the concept there. Let's see how it works. You know the answer, right? Normally also. Normally, what would be the answer? The 0 is starting here. So this is 3. So this is 2.9. This is 2.8. And this is 2.7. And this division is matching 1, 2, 3, 4. So this is 2.74 centimeters. Your regular method, you can just see and finish it off. That's not a big deal. Aditya, keep your cam on. Not really, YouTube. The other Aditya. Now see the other method. Where do you keep the object? The object will be somewhere here. Agreed? I don't know where, how far it is. Like the object will be there, isn't it? It will be between vernier calipers and the jaw. Length of the object is L. Agreed? It is starting from somewhere here. So ये 0 होगा. Which division is matching? This division is matching. So from here to here, what will be the length? That is 3. This is 3.1 centimeter. No? Do you guys agree? So you always take the measurement from the 0 to the point where the division is matching. And how many divisions is this? 1, 2, 3, 4. That means this length is 4 vernier divisions. Sure. That means the length plus 4 VSD must be 3.1 centimeter. So that is 3.10 centimeter. And here it's a regular main scale. So minus 0.36. 2.74 centimeters. Is this making sense? This is a very superior method compared to the regular one. I too won't recommend. Remember, forget about the regular one because, but I have to teach you because there are a lot of terminology. Error, that, this you should know. Clear how we did this? Now let me show you the question where they asked in advance, and you'll see why it won't work in a regular method. Why doesn't it work? There, this was a J advanced question. Read the question. Take a minute, and then I'll show you what happens with our regular method. It works. Regular method works. If you actually understood now how vernier calipers is working, you can even use the regular method. But the second method which I taught you is more superior. You need not care about anything. You can just finish it off. But read, understand, whatever you think you do. I'll give you 2-3 minutes and then I'll tell you. I'll show you both the ways. Now, I marked the red color. Huh? That is the division which is matching. The picture is not clear. आंसर तो ठीक है. Just to try and get some water and cough. Let's see the regular method. Now, he's saying there are two vernier calipers. Both have 1 centimeter divided into 10 equal divisions on the main scale. So your main scale is regular main scale. So one main scale division is 1 mm. In the welding caliper C1, you have 9 divisions equal to this thing. So one vernier scale division is also 0.9 mm. This is your standard vernier calipers. So you can just see and get your normal answer. You can clearly see this is a 2.8 and that is 7, so 2.87. But that is of no use, all have 2.87. Okay. Actually, fourth option gets eliminated, but okay. Now, if you look at the next one main scale division is 1 mm, but he's saying 10 divisions of vernier calipers is equal to 11 main scale divisions. So one vernier scale division is 1.1 mm. Vernier scale divisions are bigger. So if you actually see, the regular formulas will not work. So how do we use this? So if you want to use a regular way, this is how I have to do. So again, you have to go back to the scratch. How did we derive the regular formula in the first place? Let's draw this thing. I'm drawing for C2. It's a non-standard one. So if you know how vernier calipers works, you can still do. But like I said, the method 2 is superior. So this is your division 10. So when you try to draw the vernier calipers thing, this will be 0. This will be slightly ahead. So the 10th division of this will match with the 11th division. Everyone clear with the picture? Now you tell me, what is the distance between the first and the first division? The distance between the first and the first division is 0.1 mm. Distance between second is 0.2 mm. Third 0.3. This is all great. But if I want 1 and 1 to meet, what should I do? Should I push forward or backward? This time I should push backward. If I move this 0.1 mm backward, first main scale division and first vernier scale division will match. Similarly, if I move this thing 0.7 mm backward, 7th main scale division and 7th vernier scale division matches. Agreed? Now, if you go back to our problem, again, I won't recommend you to do this. I'm just showing you. Now look at the problem here. This is 2.8, agreed? Imagine if the answer was exactly 2.80, how will the picture look like? If the picture was exactly 2.80, the Vernier will be exactly here, na? The 0 will be exactly on 2.8. Now tell me one thing. Now you're saying which division is matching? The 7th division is matching. So if you want to meet the 7th division, I should push it back how much? 0.7 mm. But if I push it back 0.7 mm, then this will go from 2.8 to 2.7 ka beech mein, na? You're getting the problem. If you push it backward, you won't be at 2.8 anymore. You'll become 2.7 and 2.8 ka beech mein. So the thing is, you should not push it from 2.8. You'd actually push it from 2.9. So from 2.90, move it back 7 divisions, that is 0.07 centimeter. Then 7th division will match. Exam में इतना सोचना पड़ेगा. Therefore, what is the answer? 2.90 minus 0.07, 2.83 centimeters. Clear how to do this in the normal way? Still, the formula is not valid. You have to work it out. You can still make a formula. It would be something like this. It will be the main scale reading plus you have to take the main scale reading 1 unit more actually. So let's not use this. Now let me show the other method. Which division is matching? The 7th. So the object must be somewhere here. This is length L. So from here to here, this is your 7th division. So this is 7 VSD. So from here to here, this is how much? 3.6. This is 3.7. So this is 3.7 centimeter. That means length plus 7 times VSD is 1.1 centimeter. Must be, that's 1.1 millimeter. That's 0.11 centimeter is equal to 3.70 centimeter. That would be 3.70 minus 0.7. Sorry, that is 3.6 actually. Got this? Is the logic making sense? I don't care what is the division, what is that. There's nothing, no story, you don't need anything. Just put the rod length and finish it off, I'm done. But if you try to do the normal way, you need to figure out this much. That when I pull back, then they will match that division, this division. And there is no guarantee this is the last question, right? They'll make even more variety things. So then you'll start getting more messed up. But this will work. Because this thing is not Vernier calipers or anything. This is simple logic. Length plus this length must be this length. There's no option out. All clear with this? Clear? So stick to the second method. Forget about the first one. Any doubts on this? Let's see one more. Try this. You'll understand why I'm saying the first method starts becoming a problem. This is also an advanced PYQ. Read the version. Take a minute or two. It's a lengthy one. This is a good question. It covers a lot of things. This thing talks about non-standard Vernier calipers. This thing will actually talk about least count and Vernier constant. This thing also has a negative error. So when there is no object, this is how the scale looks. When there is no object, this is how the reading looks. So using this, get me the answer. Try. I'll give 2-3 minutes. Now, if you go with the regular method, you'll go mad. That is 10 Vernier divisions are matching with 4 main scale divisions. Take a minute more, then I'll show you. I hope everyone understood. This thing is not matching with one division, it is matching with two divisions. It doesn't matter. You can actually choose any division, the answer will still come the same though. Let's see. Aditya. So, first thing, 10 Vernier scale divisions is 4 main scale divisions. One main scale is 1 mm, so one Vernier scale division is 0.4 mm. So here the divisions are 0.4 mm each. How is your picture? Look at the picture it is given. Initially, when there is no object, the 0 is behind. This is a negative 0 error. Normally, negative 0 error में क्या करना था? It is actually 10 minus divisions and you don't need to do anything. Ignore all that. So your 0 is here and this 0 is here. Okay? That means, look at this. From this division is matching and it is given in the question. The fifth division matches with the first mm. You could have taken the next one also, 3 and 10, you'll still get the same. So what is this length here? 5 Vernier scale divisions. What is this length here? 1 mm. That is given, this is a 1 mm. Then what is this thing here? This is your error, isn't it? Normally 0 and 0 should have matched, isn't it? 0 and 0 not matching. So here E is your error. That is the extra distance, you have to move before you actually get the proper reading. And how much is that? So 1 mm plus error is 5 times Vernier scale division, which is 0.4 mm, which is 2 mm. So error is 1 mm. Is that making sense? That means this scale is showing 1 mm less. So whatever answer you are getting, you're always getting 1 mm less. So the zero error is taken care of. Negative error, positive error, you don't care about this. It will take care of the error. Or else you have to go back to that story. In a negative error, it will come back to 9th division will match with the 8th division. You're getting the problem there. In that way, this method is superior. You don't care about all those things. Now, coming back to the question. Now, when you keep an object, the second division, which is the second Vernier scale division, matches with the 23 mm mark. You could have taken 7 with 25 also. It doesn't matter. You get the same thing. So your second division is matching with 23 mm mark. So this guy was 20 mm mark, 21, 22. This is 23 mm mark. Great. And this is your second division. Same story. The object must have been somewhere here. Length of the object is L. This is 2 VSD. This is 23 from here. So this was 23 mm. Therefore, length of the object plus 2 VSD, which is 2 into 0.4 mm, must be 23 mm. The L must be 22.2 mm. But there is an error, right? So the final length will be, it is showing 1 mm less, so we have to add that 23.2 mm. Clear with this. And luckily, there's only one option with 23.2 mm. Ideally speaking, they should have given 23.2 plus or minus 2, 23 point plus or minus 0.6. That would have been really good question. Why? The problem here is, what is the difference between one main scale division and one vernier scale division? One main scale division is how much? Look at this. So if you actually look at the divisions here, this is how the picture will look, right? So if you actually find the vernier constant, which is one main scale division minus one vernier scale division, this is actually 0.6 mm. Okay? Now listen to the picture. Look at the picture here. So same story. 10 divisions of vernier match with 4 divisions of main scale. So 10 divisions are matching with 4. So that means 5 divisions will match with 2 mm. Agreed? So what is the length of one vernier scale division? One vernier scale division is 0.4 mm. Okay. What is the distance between the first division and the first division? 0.6. What is the distance between the second division and the first division? So from here to here, the distance is 0.8 mm. From here to here, the distance is 1 mm. What is the distance between second division and the first division? 0.2 mm. That means if you put a 0.2 mm object, the second division of vernier will match with the first division of main scale. That means I can measure 0.2 mm, right? Are you getting the point of it? That means I can measure 0.2 mm. Are you getting the catch? With this scale, I can measure an object as small as 0.2 mm. And I know that. Matlab, if I know the second division matches with the first 1 mm, the length must be 0.2 mm. Is that making sense? So the smallest measurement you can make here is 0.2 mm. Least count is 0.2. It's not 0.6. Are you getting the logic here? So if we move this 0.2 mm, right, then second division of vernier, second vernier division matches with 1 mm on main scale. Therefore, the smallest measurement you can make is not 0.6, it's 0.2. Therefore, least count is 0.2 mm. Some people now, they just saw the least count 0.6 and they mark the D answer. So in this scenario, least count is not equal to vernier constant. So be careful, both are completely two different things actually. In a standard vernier calipers, they're equal. So people think they're always equal, not sure. So the answer is B. Clear with this? 23.2 plus or minus 0.2 mm. So the smallest error you can have is 0.2 mm. So let me ask you, for this guy, tell me what is the least count and what is the vernier constant? If one main scale division is 0.5 mm and vernier scale division is 0.3 mm, I just give some random numbers. What is the least count and what is the vernier constant? Try, I'll give you a minute. Vernier constant is easy, yeah. 0.2 mm. Now, whenever you want to find the least count, now draw the picture. There is no other way. You won't be able to see it or else. So these divisions are like 0 mm, 0.5 mm. This is 1 mm, 1.5 mm, and so on. This guy, this is 0. This is 0.3. This is 0.6. This is 0.9. This is 4 and this is 5. So the fifth and the third division match. That's okay. Look at 3 there. So if you go for 3 divisions, this is 0.9 mm. That means if you push it 1.1 mm forward, the third division matches, isn't it? So if you move this scale by 0.1 mm, the third vernier division matches the 1 mm division. Therefore, least count is 0.1 mm. Clear with this? So be careful. Vernier constant and least count are not same. Least count is not 1 MSD minus 1 VSD. If you go and open a standard book, you'll always find that only, because for a standard vernier calipers, it works. Obviously, Nare. Aditya. The smallest measurement करके बोला तो इससे भी नीचे होना चाहिए. Clear with this? So this is one way of asking. Another way of asking. Read this. So someone has given you 2 triangles where I draw a picture here, say. So you drew lines here of each length of line is L and angle theta. You have 2 identical triangles like this. Using these 2 triangles, you have to construct a vernier calipers and measure the length of the rod PQ. Then what will be the least count? Read the equation. Have a look at this. Go back to the basic principle of vernier calipers. What is the basic principle? To construct a vernier calipers, you need 2 scales of different divisions. No, you need a main scale, you need a vernier scale. But here you give both of them identical. So I need 2 different scales. And there are 2 different scales. You know where? Look at the picture there. You can construct one scale on the hypotenuse, where the length of each line will be L sec theta, whereas the base length will be L. So you can use one scale like this, where the divisions are the main scale. So this will be the main scale on the hypotenuse. And you can use the vernier scale on the base. So what is the length of the divisions on the vernier on the main scale? L by cos theta. The bottom scale is L. So the least count is L by cos theta minus L. Make sense? There. That is the idea there. So somehow you need to create 2 different things. And there is a hint in this picture only. Can you see this? The hint is the second picture. So you are keeping the object here. So basically you're using the hypotenuse as one scale and the base as a second scale. So even though both are identical, the hypotenuse will give you a different length of the divisions. I know. Here we have to assume the least count is that only, vernier constant. There is no other option here. Because you don't give me any numbers or anything, so they should have said find the vernier constant, but okay. All clear with this? Take a break, come back in 5 minutes, continue from here. That's about vernier calipers. Next thing we'll see screw gauge. Any doubt so far? Chalo, come back in 5 minutes. Chala, let's start off. Next thing is your screw gauze. Yeah, again, I'm sure you must have seen something like this. Picture looks big. Screw gauze is actually kind of small. If you see the parts here, so this is your main scale. And here we don't call it vernier scale exactly, we call it head scale. And how do you rotate this? This thing actually rotates towards you. Look at the numbers here. Huh? This thing rotates this way. Matlab, you're rotating towards yourself. So when you rotate towards yourself, then you see the number 0, 10, 5, 20 and everything. And the simple reason, it's a screw, right? Think about this. You want the screw to go out. Right hand thumb rule. So if you want the screw to go to the right side, it should rotate which way? Towards your face, isn't it? So that's a simple way to remember this. That's important because once there was a question like this, a screw gauze is rotated, 20 divisions away from the observer. And people didn't understand what the hell was happening. Like they thought 20, but it was actually the other way around. So you should know which way it is rotating. The concept is pretty straightforward. Now, when you take a screw, it's a helix. What is the distance between two threads? We call this thing pitch. I hope you remember we did this in magnetic force. When you take a particle and project it at an angle theta with the magnetic field, it goes in a helix. Now here on the head scale, right, if you divide this into 100 divisions, so for every one rotation, the screw will move a distance of one pitch. Agreed. So every time you complete a rotation, the screw will move one thread or one pitch. If you have n divisions here, that means the least count is the pitch by n. Example, let's say if you have 100 divisions and pitch is 1 mm. What is the meaning of this? Every time you rotate one division, you're rotating 1 by 100th of a revolution. And that means you will move 1 by 100th of the pitch. So the least count becomes 1 mm by 100, which is 0.01 mm. Is that making sense? So if you rotate all the 100 divisions, you will complete one revolution and you will move one pitch. Sorry. And if you move only one division, that means you're doing only 1 by 100th of a revolution. Is this concept clear? That's it. That is the whole concept of screw gauze. So now when you keep the object between that and when you make it tight, let's say you have a screw gauze like this, they'll give you information of this sort. They will say pitch is 1 mm, number of divisions are 100. This is your main scale, 0. This number is 36. They'll give it like this. They'll ask you what is the length of the object. What is the length of the object? Now, think about this. This is 1, 2, 3, agreed? Tell me one thing. If it is exactly 3 mm, how will the picture look like? If it was exactly 3 mm, the picture would have looked like 0, 1, 2, 3 will be exactly on the border, and here you'll see a 0, right? Are you getting it? If it was exactly 3 mm, the head scale will show 0 and the 3 would have been on the border. So what is the meaning of this? You can see 3 mm plus 36 divisions. But what is each division? One division or the least count is one pitch by 100 mm. So this is 3 mm plus 36 by 100 mm. This is 3.36 mm. Are you clear how to do this? Clear with the screw gauze? So this is actually much easier than vernier calipers. Vernier calipers should be had some story and all. Screw gauze, there's nothing. They really can't mess it up that easily. So that's it. That is the whole idea there. Can you tell me what is the answer for these two? This thing is 1, 2. You can't see the third division. Huh? Third division is not there. So this is 2 mm plus 36 divisions. One division is 1 by 100. So this is 2.36 mm. This is 5.80 mm. You can see and tell now. Easy? Get me the answer for this. So this is a general formula. Main scale reading plus head scale reading into least count. This picture actually is like this. So I'll magnify it. You can see and guess which division is matching. Least count is 0.01 mm. And it looks a little difficult. You can see this is 3.5, 3.6, 3.7 now. That is 37 divisions. So you're done, right? So that will be 8 mm plus 37 by 100 mm. 8.37 millimeters or 0.837 centimeters. Clear with this? So Kruger's questions are pretty straightforward. There is not much variety in this. Now in this also we have errors. Normally, if there is no error, how should the device look like? If there is no error, your main scale ka 0 will be here, your vernier ka head scale 0 will be like this. Agreed? So this is the case when there is no error, when there is no object. Sometimes you'll see like this. You will see the 0 is out, and let's say this is 36. Means you can see 0, you can't see the next division, but 36 is there. What is the meaning of this? Even though there is no object, you are showing 36 divisions more. Making sense? Even though there is no object, you are supposed to be 0, but you're showing 36 divisions. That means in the final answer, you subtract minus 36 divisions. Sure. This is called positive error and the correction is negative. How do you think 0 error looks like? In case of a 0 error, the screw has gone inside, so you actually can't see the 0. 0 is not visible. That is how you know whether it is a positive error or a negative error. And let's say this thing is showing 36. Now what is the correction? Always be careful. Moment you hear negative error, it's a trap. The 0 is inside. You can't see the 0. And it is showing 36 divisions on the head scale. What is the correction? At a total 100 re Aditya. You are the kind of person, you know, वो होता है ना movies में, the heroine is going away in the flight airport में and the hero goes there. You are the type of a person who goes to the airport, heroine is just standing there, but you fight with the police and get arrested and the heroine is just looking at you. मतलब ये क्या कर रहा है? I'm standing here only. You're that type of thing. सब आंसर आके तुझे ना you have to goof up. हाँ, tell me one thing. When will the 0 go inside? If you rotate in the opposite direction, right? Now, if you rotate in the opposite direction, what number you will see after 0? 99, 98, 97, isn't it? You won't see 1, 2, 3. You will see reverse numbers. And when will you see 36 then? You will see 36 after rotating 64 divisions. Na? Are you getting it? If you rotate one division backward, after 0, what will come? Ever seen your speedometer? If you rotate backward after 0, what you get? You get 9. So from 0, if you rotate in the opposite direction, instead of 1, you'll get 99. So when you got 36, meaning you have rotated 64 divisions. So what is the correction here? Plus 64. So whatever is your final answer, you have to add 64 divisions to it. Is that clear, everyone? Ansh, clear with that? Arnav? Niharika? Clear? Saish? Vivan? Any doubts? Pratik? All clear? So then I wrote it down clearly here. So if you have no object, this is a 0 error, this is a positive error, this is a negative error. So in case of a negative error, when you rotate backward, you get 0, 99, 98, 36. So we rotated 64 divisions. So the final answer is 64 divisions less. You have to add 64 to it. Clear with this? There, that's about your one-year calipers and screw gauge. So I'll send you a small sheet also on this. Right, maybe 10, 15 questions, you can do that much. But advanced scale important. Every year, advanced may one question is for sure. Directly nahi hai. Generally they mix up with errors and stuff, but they do ask pretty good ones. That is the main topic today. The next thing, we got more theory. In this, there are no derivations, nothing. It's all direct results only. You need to mug it up. So listen carefully. Diffraction is still important. Unfortunately, I can't prove you so much, so I need to show you a lot of things though. So first thing is diffraction. This is also called as a single slit experiment. I'm sure you must have heard this word while you're doing some questions. What is double slit experiment? YDSA. That's your YDSA is Young's double slit experiment. A single slit experiment is your diffraction. So what is diffraction exactly? It is the bending of light rays at the edges of an obstacle. So whenever light rays go through an obstacle, right, in certain cases, the light rays, right, will start bending. So we have two cases here. One, when the slit is large. So you have a large slit and you send the light rays, nothing happens. The light ray almost goes straight. Right? But when they make the slit very small, or when A is comparable to lambda, you actually see the light ray deviates a lot. So this phenomenon of the light ray bending at the edges of an obstacle is called diffraction. This is the first question. This came in CAT. Which of the following condition must be satisfied for diffraction? Lambda greater than A, lambda less than A, lambda almost equal to A. This is your first question in diffraction. So when the wavelength of the slit and the wavelength of the light and the width of the slit are almost equal, you get maximum diffraction. So what is this diffraction exactly? Let's see something.
Look at is what happens to a water wave when it passes through an aperture. Well, I fitted an aperture here, but it's rather too wide.
So here he is using water waves, and that slit which we have is our aperture. So there's a big one.
I need at the moment. So if I fit these sliding doors, I can make an aperture that's
you can make it bigger or smaller using this.
About 3 centimeters across. And if you now look at the screen, you can see that as the waves pass through the aperture.
Can you see the edges, how they're spreading? The beam which is coming, it's just not going straight, but you can see the edges, right? The whole thing is spreading out.
They spread out. This spreading out of the wave as it passes through an aperture is known as diffraction, and it's a property of all types of waves. So what do you think controls how much the wave spreads out? Well, one possibility is the width of the aperture. And what do you think would happen if I made the aperture smaller? Well, you might be surprised to learn that a narrower aperture leads to more spreading out of the wave.
Actually, it spreads out even more in this case. So the thing, why you don't see this in real life is because when light passes through your window, what is the light ka wavelength? 4,000 angstrom, 7,000 angstrom, visible light, right? What is the length of your window? 1 meter, half meter, 10 centimeters. So the size of your window is too big compared to the wavelength. So when the light comes through your window, it almost feels like it goes in a straight line. You don't see this bending. Getting it? So normally diffraction, you see it in sound waves to an extent and water waves, because in this thing, if you see the wavelength, can you see the wavelength here? What is wavelength here? The distance between two troughs, isn't it? So in this picture, in the video, can you see there's a trough cut distance? That distance is almost equal to the width slit of the, the slit ka width. Can you observe that? So when the wavelength is almost equal to the slit ka width, you get maximum diffraction. So you can clearly see this in water waves because the wavelength is in centimeters and meters. But light, you can't see this. So day-to-day life, you don't see this because the wavelength is just too small.
Diffraction. If instead I make the aperture wider,
if you make the aperture bigger, the spreading decreases.
then after it's settled down, you can see that the wave becomes less spread out. The diffraction is less pronounced.
So he did try with an experiment with a small slit of light.
Causing much diffraction seems to imply that light.
The slit is big, so you don't see much of there.
I need to use narrow
So
range.
they're using a very narrow aperture with a laser.
So if I place this slide action pattern, spot
This is your YDC pattern, if you remember.
in the pore structure, if I use some spreads on each side, swap again one. Pattern with the rainbow and blue light the
You're not
shortest.
clear. I'll post it anyway. There. So clear with this thing. So whenever your aperture ka size and wavelength is almost equal, you actually see the light rays deviate a lot. This phenomenon is called diffraction. So this is your question. 1 lambda is equal to A. That came in CET. Second thing, we have two types of diffraction, Fraunhofer and Fresnel. Now Fresnel is not there in the portion. Fraunhofer is there. What is the difference between them? In Fraunhofer diffraction, the distance between the screen and the slit is large. In Fresnel, the distance is small. So we won't be studying Fresnel anyway. So how does this thing work? So you send a parallel beam of light onto the slit. So, and then you put a lens there. When a parallel beam falls on a lens, it meets at the focus. So here, the focal length is the distance between the slit and the screen. Getting it? So that itself also they ask questions on that. In a Fraunhofer diffraction, a lens of focal length 20 centimeters is used. So indirectly is giving you the capital D ka value. Okay. Now again, like I said, we don't have any proofs or anything. Even in NCERT, results are dumped directly. But let me try to explain a bit. So how do we study this? See, so when we have this aperture, we have the screen here. This is the idea behind the derivation. So we can divide this entire aperture into, infinite small points. Did you ever see an LED like, this traffic lights ka headlights, lights? The whole thing is made of multiple LEDs, isn't it? Something of that sort. So you can assume this big slit which you have actually consists of multiple light sources, all point light sources. Okay. Here, choose any two light rays. So choose two sources at a distance of A/2. So I can assume now the light is going from this point and this point. And now this thing looks like a YDAC experiment, isn't it? So if you consider any two light rays at a distance of A/2, so this thing is like your small d, right? And that is like your YDAC. So from here, if you drop a perpendicular, this will be your extra path difference. And if this angle is theta and this is theta, the path difference delta x will be A/2 sine theta. Then what you do, you take one source below, means you go one step below, and you go one step below. The distance between these two is also A/2, agreed? And from here to here, the path difference is again A/2 sine theta. Make sense? Then go one step below. That is also A/2. One step below, that is also A/2, 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 A/2. So if you see, when you take 2, 2, 2, 2 points ka thing, all of them have a path difference of A/2 sine theta at the same point. Sure. Because the slit is small, you can assume the angle is almost same. Now for this, if you take λ/2, this is your first minima. If all of them have destructive interference, the difference will be λ/2. That is your first minima. Then you'll get a dark spot here. Now, why do we study dark spots? Because when you have a non-uniform intensity, it is more easy to see dark spots than the bright spots. So we prefer to study dark spots. Then what they do, instead of A/2, now we take A/4. Then again, I do the same thing, interference. This time it will become A/4 sine theta is equal to λ/2. I get a second minima. third minima, and so on. So when you do this, there. So each point on the slit can be treated as a point light source emitting from the wavefronts. So diffraction is actually interference of all these point sources. YDSC is an interference of two sources. Diffraction is an interference of infinite point sources. You can think of like that. And when we do this, the path difference is a/2 sine theta. We end up with these two formulas. So sine theta is equal to n lambda by a is your nth minima. 2n plus 1 lambda by 2a is nth maxima. Clear with this? This is your second important formula. You get again straightforward questions. In a single slit experiment, find the position of the first minima. Sine theta is equal to n lambda by a. Direct questions. They really don't ask anything more than that. This is your second question they can ask you. Clear with this? Then when you look at the intensity, this is another important graph. This is a graph between intensity and the fringes. You will observe the central fringe is actually the brightest fringe. Let me show you how the picture will actually look like. You can look at this picture. This is how diffraction pattern forms. And can you see the center one, how big it is? So in case of a YDSC, if you remember, all the fringes in the center are almost equal width, isn't it? Lambda capital D by small d. But in diffraction, the central fringe is 2 times the thickness. And the fringes don't have same intensity also. The first central fringe will have intensity I, next fringe will have I by 22, next fringe will have I by 61. So in a way, if you think about it, your eye is actually a single slit, isn't it? If you close one eye and see something, isn't your eyeball a single slit? So the light entering into your eyeball also undergoes diffraction. So that means when you see something, technically, you should be actually seeing not one, but images one top of another, isn't it? Means if I try to look at you, you should look like this. You are like this, and there is one more of you surrounding, and there is one more surrounding you. But the reason you don't see all that is because look at the intensity drop. It dropped by almost 20 times. It becomes too feeble. You can't see that. So our eyes can't detect it, but normally if you use very powerful telescopes or microscopes, they have these issues. So what are the important points in this? The central fringe width is 2 lambda capital D by small d. You should mug up this result. Unlike YDSC, the fringes are of not a same width. The central fringe will be double the thickness. The remaining fringes will be same, lambda d by a. A is the width of the slit. The angular fringe width is 2 lambda by a. So that is the main thing. The fringes are not of equal intensity and fringes are not of same width. And the central fringe is 2 lambda d by a. This is your third result. Clear with this? And once you know the path difference, delta x, how much is delta x? We derived here, a by 2 sine theta. I can find the phase angle, which is 2 pi by lambda delta x. And then intensity ka formula is given by this. Not that important, little rare, but there. And then there is a question like this in the exam. If the width of the slit has become doubled, what happens to the intensity of the central bright fringe? This is an important question. What do you guys think? If you make the slit ka width double, what happened to the intensity of the central bright fringe? Do you guys remember in YDSC, if you make the slit double, what happened to the intensity of the slits? Intensity is proportional to the area of the slit. Yeah. So here what happens, I'll tell you. See, if you make this double 2a, what happened to the fringe width? It becomes half, right? And if you make the area double, then what happens to the power? Double. Now think about this. When you made the slit ka width double, power became double, but the area became half, the area of the fringe. And what is intensity? Power falling on a unit area. Power doubled, area became half, intensity becomes 4 times. Clear with this? The power of the slit doubles, so intensity becomes 4 times. Sure with this? That's your fourth question. Again, what is the first question? A is almost equal to lambda, you'll get diffraction more clear. Then sine theta is equal to n lambda by A is for minima. Third one, central fringe width is 2 lambda capital D by small a. The fourth one, if you make the slit double width, the intensity becomes 4 times. The next one. This is another question they asked. What is the phase angle between the two light rays going from the two corners of the slit? Now remember, just now I showed you the derivation. So at this minima here, so if these two light rays are forming a minima, what is the phase angle between them? If this is 0, this is phi, na? Because they're forming destructive interference. Similarly, if I take this point and this point, these two are also forming destructive interference. Then what must the phase difference? That also must be pi. So it must become 2 pi. That means what is the phase difference between the two light rays from the two corners? 2 pi, isn't it? Are you clear with that? They're in phase. That was one good one. So the rays from A to B form destructive interference. Rays from B to C also form destructive interference. That means from A to C, they must be in phase. This is your fifth question. Clear with this? This is how the shape will look for a circular slit and a rectangular slit. So for rectangular slits, you get rectangular slabs. For a circular slit, you get these rings. The last one is called Fresnel distance. So what is Fresnel distance? The distance of the screen from the slit so that the spreading of light from the center of the screen is equal to the width of the slit. What do you mean by that? So when you take a slit here and the screen here, the light rays will spread. So what Fresnel distance is, the spreading of the light wave must be equal to the width of the slit. Meaning this must be A by 2, this must be A by 2. This is the total spread, no? If there is no spread, you would have gone straight. Because of the spread, you got expanded. So the spread must be A, and this distance is A. And we know this is your central bright fringe, so this must be 2 lambda d by A, which is 2A. So we get d is equal to A square by lambda. This distance is called Fresnel distance. So what is this exactly useful for? Tell me one thing, a microscope works based on ray optics or wave optics? Again, while forming an image, do you assume the light is going in a straight line like a particle, or you assume it is going in a wave? Particle nature, isn't it? Entire ray optics is based on that light is a particle or it's like a light ray, it is a ray nature, getting a particle nature. So that means you won't have diffraction, stationary waves, all this stuff won't be applicable. So when you are working on a microscope, right, you have to make sure the object is placed within the Fresnel distance. If the observer is within the Fresnel distance, diffraction is less. So you won't see diffraction. So imagine you're looking at a bacteria, and if you're looking from really far, what will happen? Because of diffraction, the bacteria will get distorted image. You can't see it clearly. So whenever you're operating microscopes, right, or devices which have high accuracy, you need to make sure the device is working within Fresnel distance. Once you exceed Fresnel distance, the light rays will divert so much, the ray optics will not be valid anymore. Clear with this? That's it. There's nothing more on that. That's called Fresnel distance. Again, totally how many are there? A is almost equal to A. Lambda. Sine theta is n lambda by A. Central fringe width is 2 lambda d by A. Intensity is not same, right? The fringe widths are different. The central fringe will become 4 times if you make the slit curve width double. The phase difference between the two light rays from the edge is pi. Fresnel distance. Almost 6 questions. Like I said, a lot of theory, na? And look at the questions. This is how they'll ask questions. Plane microwaves are incident on a long slit of width 5 centimeter. So he gave you A ka value. The wavelength of the microwaves with the first diffraction minimum is 30 degrees. So he gave theta. Sine theta is n lambda by A. Straightforward questions, huh? Matlab, people just don't remember the results and they're gone. The questions are also not that frequent actually. They're little rare, but if they ask, it will be pretty straightforward. So for this chapters, not diffraction and dispersion, next thing, just go through the notes and finish your PYQ. Sufficient, that should take care. Look at the second one. A screen is placed at 50 centimeters. So this is capital D. Illuminated lambda. The distance between the first and the third minima is 3 mm. So done, no? Sin theta is equal to n lambda by a. Right? Put n is equal to 1, put n is equal to 3 and subtract them. That must be the distance. A slit of width D is placed in front of a lens. There. This is a different one. Focal length is there. So this is capital D. The first diffraction minima on either side of the central maxima are separated. So this thing, the width of the slit, this is actually 2 lambda T by A. He gave the central fringe width. Other questions clear, everyone? Straightforward. But please make sure to go through this once. That's about your diffraction. So revise the notes once, right? I'm sure you'll understand most of it. Just do your PYQ sufficient. You're still confused, ask me. I'm going to do these questions again. In January, I did keep 2 sessions for these things only because I'm pretty sure you guys will forget. But that's what I'm saying. Within this week, not too much, just do 15 to 20 questions, sufficient. If you do at least 10, 15 questions, you'll remember, you'll not forget this thing. When we revise again in Jan, you'll remember easily. But if you don't do anything, Jan May, you will say, I have seen this somewhere. It's like your long lost twin brother. Or movies mein hota hai na, your twin brother was lost, or twin sister was lost. Rowdies are chasing your parents and one kid has to be left over and the other kid has ran away. So aisa kuch ho jayega. So let's not know that. The last thing, dispersion. These questions are rare, but CET may they do ask one question pretty frequently. So we'll see that. This is your standard prisms. We have done this before, right? Deviation is I plus E minus A. A is equal to R1 plus R2. All this stuff. I hope you remember this formula. This was important. And this is there for advance also. So mu is equal to sine A plus delta M by 2 by sine A by 2. Now for thin prisms, when A is less than 5 degrees, the deviation becomes A into mu minus 1. Till here, the story is common. You have seen this before. Anyone remembers recently we used this formula in some chapter? Which concept? Anyone remember where was the last time we used this thing recently? Anyone remembers? Or when was the last time you remember using this delta is equal to A into mu minus 1? Wave optics में कहाँ पे? Semiconductors में. Semiconductors में, where did you use this thing, right? Prisms. I know you're hungry or you're sleepy, but right home. Thin film नहीं रे अंश. Thin film prism कैसा होगा? फिर भी ठीक है, तेरा answer much better है. Someone said modern physics semiconductors. Good thing didn't say kinematics. Wave optics. Fresnel biprism experiment याद आया? ओए ये important है. It's a 4 marks HSC boards का question था ये. If you're an HSC board, this is a 4 marks HSC derivation, this whole thing, don't forget. Okay? Now, listen, this is something new from here. Cauchy's law. Cauchy's formula says the refractive index is A plus B by lambda square. So till now, we thought the refractive index depends only on the material. But in reality, mu also depends on the wavelength of the light. Now, we don't know exactly what the, the numbers and relation, but the formula is A plus B by lambda square. A and B are constants. That means higher the wavelength, lesser the refractive index. So light of different colors will have different refractive index. So who has the highest wavelength? Red. That means mu of red is the least. Clear with this? So how does this affect our problem? Now look at this. So when you take a prism, angle A, thin prism, I'm using this black line for white light because white light you won't be able to see. What is the deviation? A into mu minus 1. And the lambda of red is greater than lambda of violet. That means mu of red is less than mu of violet. Therefore, deviation of red must be deviation of violet. Agreed? That means whenever you send the white light has multiple frequencies, multiple wavelengths, so all of them won't have same deviation. So the light ray among all of them, the violet will have maximum deviation. And who will have the least deviation? Red. And you get all the remaining colors in the middle. So in school, if you had remembered, right, you must have taken a scale and you must have played in the sunlight. You get a rainbow. Ever did that? Maybe not a rainbow, but at least 3-4 colors you must have got. When you put your scale in the sunlight and if you put it at an angle, you can see colors on the bench. So, getting it. So this is the reason actually you get a rainbow also. When you have these water droplets in the sky, right, and when the sunlight falls on it, the light splits. And that's what you see as a rainbow thing. So this phenomena of the light ray, dispersing into its individual wavelengths or something is called dispersion. Okay. Now here again, a few formulas there. If you take the angle between them, theta, this theta is called dispersive angle. Dispersive angle is nothing but the angle between delta V minus delta R, the difference in deviation. So Devan, stop talking now. Someone is typing non-stop. I don't know which Devansh is this though. Wait, I'll kick you out so we will know who it is. Random talks. Prism experiment. Kya sabji kha rahe ho? What is this? So this is your theta is your dispersive angle. Okay. And what is delta V? This will be A into mu violet minus 1 minus A into mu red minus 1. So this becomes A into mu violet minus mu red. This is the dispersive angle ka formula. Then we define something called, this thing looks like omega. This is called dispersive power. These are the two main formulas. So dispersive power is nothing but dispersion angle by the average deviation. In this case, it's delta violet minus delta red by, we either take delta yellow or we take the average delta violet plus delta red by 2. Then your formula becomes mu violet minus mu red by mu v plus mu r by 2 minus 1. This formula is called, right, the dispersive power. So these are the two formulas and this is how we derived. Are you getting what is dispersive angle? The angle between the two extreme light rays. What is dispersive power? The angle dispersed by the average deviation. समझ में आ रहा दोनों formulas? There. So these are the formulas. So delta V minus delta R, mu into this delta theta by delta average, which is delta V minus delta R by LO or average. And how will ask questions? Look at the numbers. Straightforward. They'll give you the numbers. You have to just dump it there. Have a look at this once. Then I'll show you. So again, I know prism angle 10 degrees is not small, but there's no other option. So he's asking, this is a ka value is given. This is mu red and this is mu violet. You can see the difference is actually very, very small. That's why we ignored it. But here it comes. So find the dispersive power. What is the formula? You know the formula, dump it, you get the answer, you're done. That's it. There's nothing there. If you know the formula, you'll get the answer, or else you're wrong. Mu violet minus mu red by mu average minus 1. The refractive index of a flint glass for red and violet are given. So mu red and mu violet are given. Find the dispersive power. Same formula, dump it there. Clear with this? I know this is exhausting, so you're almost done. Next thing, what happens if you put the prism in the reverse? If you put the prism in the reverse and you send the black light with the white light, so blue goes, the red comes down and the blue goes up. So basically just reverses. So now what happens if you put two prisms together? So we have two combinations here. So you put two prisms together. Let's call this thing angle A and let's call this thing angle A dash. So case one is the average deviation is 0. But there is a dispersion. What do you mean by average deviation? You send a white light, the beam spreads off. So technically speaking, there is deviation. But if you take that yellow color, right, the average, I'm drawing yellow. So this yellow light and the initial light ray are parallel. There is no deviation. So that's what we call it average deviation. If the average deviation is 0, then this is our first case. This is how it looks. So you have no average deviation, but there is a dispersion is present. So if deviation is 0 means what? First prism will give deviation delta 1. Second prism will give deviation delta 2. Add them. What is deviation? A into mu minus 1. So A into mu yellow minus 1. A dash into mu yellow dash minus 1. Remember, both the prisms will have different materials and different Eka values. So if you solve this, you will get Eka value. So if you want average deviation to be 0, the angle of the prism must be this. And the negative indicates prism is inverted. These things are, I don't think you'll be able to remember these things. You should actually know that how to derive this. Little low priority, but do keep in mind, if you're done with everything, then you should definitely do this. Because this might pop up in, that other exams, CET may or Manipal or all those exams, it can pop up, or bits maybe. The second case, there is no dispersion, but there is a deviation. This is a little better. So if you send a light through this, the light rays will spread, and then light rays, this second lens, second prism will converge them, and you get back again white light. So one is spreading it, one is compressing it. So that means whatever is the dispersion here, theta, this will be minus theta, isn't it? So one is expanding and one is compressing kind of thing. So here the net dispersion is 0. And what is dispersion? Delta V minus delta red. What is delta? A into mu V minus R. So if you have this angle, if you send white light, you get white light outside. These are the two cases. Deviation 0, but there's a dispersion. There's a dispersion is not there, but deviation is there. You can't have both 0. And to get both 0, what should happen? It should become a parallel slab, no? If it becomes a parallel slab, then what will happen? If you send a light ray, it will come out parallel just with a lateral shift, remember? That is only possibility. Then it can happen. And have a look at this. This is how the question will be framed. So look at this thing. So one of flint glass and other is crown glass. So they have different muka values. A cup flint glass is given, mu is given, mu is given. Omega is the dispersive power. This dispersive power is given. So the first case, you're saying the average deviation is 0. So delta plus delta dash is 0. This is the formula. And that's your net angular dispersion. Net angular dispersion is theta plus theta dash. So you can check it out. So it is just all formulas. This is important. This will be mostly there in CET. Chromatic aberration. Do you guys remember where we heard the word aberration before? Spherical aberration, yeah. When you send parallel light rays onto a spherical mirror, they don't meet at the focus. It's a property of a parabola. Now look at here. If you take a lens, what is the focal length of formula? Mu lens by mu medium minus 1 into 1 by R1 minus 1 by R2. And now you're telling me the mu of red is less than mu of violet. That means focal length of red is greater than focal length of violet, na? Means if you send a parallel white light into a lens, the red ka focal length is more, so the red light will actually get separated and they will meet here. Not much, but they will do separate, and the blue will again separate out here and meet somewhere here. That means you will find not a single image, but a distorted image. Now think of extreme case, okay? Imaginary case. If I make you stand there and if a light actually splits, imagine there are 7 to 8 people of you, same thing, but different colors. There is a red color version of you, blue color version of you, green color version of you. There are 7 colors of you. A rainbow person type. There is one cartoon episode, of this Aladdin and Genie. Something happens to Genie and Genie becomes 7 different color ka Genie. So something of that sort. So this error is called, chromatic aberration because it's coming because of this light and all. So how do we encounter this? So let's see, normally you don't have a problem, but if you're making very powerful telescopes, this actually becomes a big issue. If I use a biconvex lens, then biconcave lens, then what will happen? This will diverge. Same story, when you extend it backward, this will be the red ka focal length. This is the blue ka focal length. Now, what if I can combine both of them such that this guy, the red will push forward, here the red will push backward. If I can somehow cancel them out, won't the light rays just go normally and meet? So that is what we do. This is called achromatic combination. You should definitely mark up this formula. Even at a mains, in this entire dispersion, you can't remember anything, at least remember this. This will come a lot. This is called achromatic combination. This, what it will do, it will make sure all the light rays meet at the same point. You don't get a distorted image. And this is the formula for that. Omega is not angular velocity, remember, dispersive power. Omega 1 by f1 plus omega 2 by f2 is 0. This focal length is positive because it is converging, and f2 is negative because it is diverging. There have been questions on this. They gave omega 1, they gave omega 2, they gave f1. They asked to find f2. Some places they asked to find f equivalent. After getting f2, I can find f equivalent. Combination of lenses. Clear with this? So here again, totally how many formulas are there? Delta is a into mu minus 1. That is okay, that you know. Dispersive angle, dispersive power. Condition of prism, no average deviation. I won't say remember the formula, but remember deviation is 0. And deviation ka formula you know. Then no dispersion, but deviation is there. This is the fourth one. And achromatic combination, 5. So there are 5 formulas here, and there are 6 formulas in diffraction. That's a big chunk there. Clear with this? There. With that, we're done with dispersion, and we're also done with our topics. Right? I think mostly we're done with everything, whatever is there. Maybe if there is something left out, or if I remember something later, I don't think so. But if there's something, we do have enough sessions. I did keep even 3 sessions buffer in the end also. We will finish out